attention. I'm happy to take any questions you have.
Thank you very much for this very nice talk. Are there any questions? I mean, if not, I can ask, but I think it's a very naive question. So in the beginning, you spoke about Gauss law, and I don't exactly connect like the typical Gauss law relating charge and electric like fields like to what you've shown here in this talk.
Right. So the electric field terms here essentially live on these links, and Gauss's laws essentially are a product of these link operators, and it conserves the flux flowing through this lattice. And that's how we implement Gauss's laws in gauge theories.
I see. Okay. Okay. I don't have other question, and I see there are no other question. So I will thank you very much for your very nice talk, and we'll welcome the next speaker, Whitney.
Thank you.
Hello, can you hear me okay?
Yes, so
yes,
it's
good.
my pleasure to introduce you, Rob, who I worked with at the Nell Institute. So Rob is now a permanent researcher at CNRS at the University of Grenoble, and is going to tell us about, revisiting Maxwell's work, Maxwell's demon with the quantum trapdoor. So the floor is yours.
Okay. So I should just check. I have half an hour, right? Because I think in one version of the program it said 15 minutes, but so...
Half an hour, including questions.
Fine. Yeah, perfect. Okay, good. So let me start my clock so I don't get lost. So thank you very much for the chance to give this nice talk and to enjoy these online workshops. I think it's one of the first online workshops I've been to since COVID times, and I think it's a really good initiative to have these talks where we don't have to spend hours in aeroplanes to all meet. I'm going to talk a little bit about Maxwell's demon, and I'm going to give a sort of historical view, maybe, of a type of Maxwell demon that Maxwell talked about, but then didn't get maybe as much interest as the usual Maxwell demon. And it's a Maxwell demon that's based on a trapdoor. And then I thought I would bring it up to date with a quantum version of this demon, which in principle could really be built now in experiments. And then see why it does not violate the second law of thermodynamics. So there'll be no big surprise. It won't violate the second law of thermodynamics. But I think it's interesting to think about why. And I don't pretend there's anything particularly original in this work. I think the methods that I'm talking about are pretty standard, but it maybe the model itself is slightly different. But the methods, I guess most of you will have already seen, either classical or quantum versions of it. We expect that the second law of thermodynamics holds for basically all systems, in some version or not, because otherwise perpetual motion machines would exist. And we don't see perpetual motion machines around us, so we assume that they do not exist. But sometimes you can have these things that are like illusions of violations of the second law. And sometimes these illusions can be very good, and it can be quite hard to understand why it does not violate the second law. And in some cases, it's required changing exactly how we think about the second law and adding information and things like that. But in other cases, it's not. It's simply... do you see my... Do you see my slides?
No, we don't.
Sorry, I should have...
Oh, yeah, I thought you were speaking without slides.
Yes, no, so I was showing the title, but that was the only thing, and then I suddenly realized, so let me try and share. I think somehow I tried to share and it didn't work. Okay, so... Okay, so this is a title, that there should be no work from equilibrium fluctuations. Do you see my slide, or do you also see the Zoom window on top of it?
No, we see it's perfect.
Okay, perfect, great. Sorry. Yeah, so I'm talking about a Maxwell demon. So let me maybe go to the overview. So we expect that perpetual motion machines don't exist because we don't notice them. And so that's our main reason, let's say a practical reason to think that things do not violate the second law. And so now I want to give examples from going back 160 years now to Maxwell's proposition of the demon of things that could break the second law of thermodynamics or could apparently break the second law of thermodynamics. And he actually proposed two things. One is an intelligent demon who actually observes microscopic motion inside the gas, and this is the one we all know very well. But he was also thinking about mechanical analogues of such a demon that could be actually built with technology or existing technology or future technology, and they're all based on some sort of microscopic measurement and feedback mechanism. So that's the unifying feature between both intelligent demons and mechanical demons, is that that they all have to make some sort of microscopic measurement followed by some sort of feedback on the system based on the result of that microscopic measurement. And of course, and we've heard some already, I think we've heard some nice talks about demons. There'll probably be some more this week about all the useful things you can do with them in principle, or the physics that you study when you look at these sorts of demons helps you understand physics in a whole bunch of things of cooling and generating work and so on. So I thought I would go back to one that Maxwell talked about, which is a sort of stupid demon. So he has this quote that I put at the top of the slide that I actually can't read because the Zoom window is on top of it for me. So I'll let you read it. But it's the idea that you have a valve acting as a demon. So something that lets particles go in one direction but doesn't let them flow back in the other direction. And so this was in one of Maxwell's letters to Tate. He said, actually, the demon doesn't need to be that intelligent. It just needs to be something a bit like this. And so then it was later by Smoluchowski talked of more in terms of a trapdoor, but it's the same idea. So you have some sort of one-way valve, so it can only let particles go in one direction. So the idea here is so here's the trapdoor. Can you see my mouse? Maybe
Yes, we
not.
can see it.
Yeah, okay, good. So on the left, there's this picture of the trapdoor that's closed, and a particle is hitting it from the left, coming from the right, and it's bouncing off the trapdoor. But when a particle hits from the coming from the left, it can push the trapdoor and it has a chance to go through. Of course, often it will still be reflected back, but it has this chance to go through. So that breaks the symmetry. So you have, in principle, a low probability to go from right to left and a high probability to go from, or a higher probability to go from left to right. So this extremely simple device, which you maybe wouldn't necessarily think of a demon or a measurement feedback device or anything like that. There's nothing intelligent in this. All the degrees of freedom are what are shown in the picture. And so you can write down a simple mechanical model for this, either in a classical or quantum setting. But it is still, this trapdoor in some way is measuring the particle's position and providing some feedback, in the sense that a particle, the trapdoor responds in a way, or is pushed by the particle in a way to respond that it either lets the particle through if it's coming from one side, or doesn't let it through if it's coming from the other side. So it's a measurement feedback device where you don't need to inject any energy. There's no amplification effect. It's just a simple asymmetry. And so this thing created a lot, for probably nearly 50 years, created a lot of discussion in the community, often of people who weren't quite physicists, but more engineers who maybe or people who were maybe self-taught, who hadn't fully understood thermodynamics, and people submitting patents and all sorts of things. Someone even convinced to get a big grant from the American government to build a machine that would make energy from this process. So why in principle could this system make energy? Well, it's because if you leave it running long enough, if it worked, then all of the particles would end up on one side of the trapdoor. And so you would have a large pressure difference, which you could then use that pressure difference to drive a motor to generate electricity or whatever you wanted. So it's clear this is in principle a device that could be used to generate work from nothing. So clearly violating the second law. It's going from a high entropy state to a lower entropy state. And so then what Smoluchowski claimed nearly 50 years later, which more or less killed all of these ideas, is, but you forget that if the trapdoor is sensitive enough that one particle hitting it can open it, then it should have a mass that is similar to the mass of the particles. And it should then also be undergoing thermal motion. So the trapdoor will be bouncing, it will be open and closing all of the time, because it will have the same amount of thermal motion as all of the particles. And so this sort of seemed to convince everyone that this device shouldn't work and that the second law would be restored. But so this paper is written in German, and I used Google Translate to try and translate it. And as far as I can tell, and I might be wrong, I'd be very happy for a native German speaker to read it and tell me if I'm wrong. That's all Smoluchowski says. All he does in the end is calculate the amplitude of the oscillations of this sort of trapdoor type thing. But for me, that's not quite enough to prove that this doesn't work. Because even if the trapdoor is open 90% of the time because of these random movement, if it's even closed 10% of the time, 10% of the time you should still be getting an asymmetric effect. And even if 1% of the time you get an asymmetric effect, you will in principle be breaking the asymmetry between particles moving to the left and the right. And you will have a buildup of particles on one side of the system, a buildup of pressure, which even if it's very small is already, you're going from an equilibrium state with the same pressure and the same temperature on both sides to a state where the pressure is slightly higher on one side. So clearly you are violating the second law. So one needs a more subtle argument to say why this doesn't violate the second law than just saying, oh, the trapdoor is in motion. And I haven't seen that more subtle argument that I will give to you towards the end of this talk. And I'd be very happy if you tell me that sometime in the last 110 years, someone has published it somewhere, because I'm sure I haven't looked in all of the places I could have looked. So I will give you, I'll give you my argument for why this trapdoor cannot violate the second law a little bit later. And if you want to think about it while I'm talking about some of the details here, you're welcome to, and to skip the technical details that I will now talk about. So, here's an example of a macroscopic version. So I don't know if this video is working on your screens. So this is a macroscopic version I made of a trapdoor with some beans, dried beans, and a trapdoor that's about 1 centimeter long. The trapdoor and the dried beans all have about the same mass, so the trapdoor does indeed open when a bean hits it. And when you play with this thing, quite often you can shake it. So then to imitate temperature, you have to shake it like crazy. And quite often when you shake it, you do find that when you start with equal number of beans on both sides, at the end you get many more beans on the side, on one of the sides. So that you are at the macroscopic level with this fake temperature, which you make by shaking it, you are indeed violating you are somehow violating the second law. So of course, this isn't a real violation of the second law, because shaking something is not the same as thermal excitations. So there's many reasons why this doesn't prove anything, but it gives you a good intuition to why people thought this would work, why this would violate the second law. I think you already in this little video, you can see particles going from left to right, but you can't see any particles going from right to left. Okay, so then the only thing I managed to find of people studying this trapdoor in detail was there was Zurek and so Skorodos and Zurek had made a computer simulation of the classical version of this trapdoor, and of course their computer simulation verified that it did obey the second law when they ran it for a very long time. But of course, a computer simulation is not the same as analytical proof that it can't violate the second law, because there's always error bars on any numerical simulation. So this led me to thinking about this problem, led me to think about a quantum version, because that's my domain of expertise. So I tried to cook up a simple quantum version of the system, which I think is simpler than the classical one. So it's also easier to treat than the classical one. There's less complicated mathematics, but there's a little bit, for those of you who aren't used to quantum systems, there's a bit of formalism that you need. So I will go through that quickly. So the basic idea here is you say the trapdoor is a two-level system. So the trapdoor only has two possible states. It's either open or closed. Okay, so now already you've simplified the problem. It doesn't have a continuous degree of freedom. It just has two possible states with a transition rate between them. And so the trapdoor in my picture is this blue system. And so there's a lower energy state, which is the trapdoor closed, and there's a higher energy state, which is the trapdoor open. So I called them C for closed and O for open. You maybe want it to relax naturally down to its lower energy state. So you might want it to be interacting with a bath that absorbs energy so that it can relax. Otherwise, a quantum system that doesn't couple to a bath will stay in. If you excite it, it will stay excited forever. So we don't want that. So then I have I have my left and my right reservoir of particles, and I imagine they're electrons. And then I have a single level between them, and I have tunneling from the left reservoir into this single discrete level. And in principle, I have tunneling between this level and the right reservoir, but only if the trapdoor is in the open state. So the reason this can be implemented in an experiment is that electrons in quantum dots, which is what I'm thinking of, repel each other. So if this low energy state in this quantum dot is close to this point where these two, you tunnel from dot A into the right reservoir, if it's close enough, it will actually repel the electron and stop it tunneling. Whereas if it gets excited into its higher energy state, if that higher energy state is physically further away, then it will be there will be a less repulsion between the electron that's physically further away from this dot, and now electrons will be allowed to tunnel here. So in reality, it probably won't be an all or nothing effect. It will probably, the tunneling rate here will depend on whether you're in which of these states you're in. But already you modify the tunneling rate, and then you can use some physics of screening to say that an electron coming from, then there's one more ingredient that you need, and that is when a particle hops onto this dot, then it needs to be able to open the trapdoor. So it transfers energy to open the trapdoor. So you can arrange also that because of the repulsion between the electron and the electron in this dot and the electron that is forming the trapdoor, so that when it arrives in the dot, it repels this guy and tries to push it into its excited state, which is the open state, and then it can tunnel through. So that I think I drew here. So you have a particle coming from the left, it tunnels into the dot, it repels the trapdoor, so the trapdoor gets excited, and then it's allowed to tunnel into the right reservoir. An electron coming from the left reservoir, you can arrange it so that there's a screening effect when electrons are inside the reservoir, which is known in these nanoelectronic systems, so that it doesn't repel this trapdoor enough to be able to do the reverse process to hop back again. So this is all quite little bit complicated, but it's still probably at least mathematically, a bit simpler than the classical version, because it's just it's basically a four-state system. This dot can be empty or full, and this electron can either be in the level C or in the level O. So and similar things, not quite as complicated as this, but nearly as complicated as this, have been built in various experiments. So they're really doing experiments on these things using this electronic repulsion to do interesting sorts of effects that are very similar to this. So I think in principle, it should be possible to make this system. So then there's some ugly Hamiltonian, which you can write down for this system. So this is probably I can skip it, because those of you who know these sorts of systems know this, and those of you who do mostly classical thermodynamics probably don't want to learn this ugly Hamiltonian from this talk. So there are terms in the Hamiltonian related to the energies on each dot, and there are terms related to the tunneling between the reservoirs on the dot, and so on. So I put some arrows showing some of the terms, but maybe let's skip that. And then there's basically two ways you can treat this. One is to do a Keldysh diagrammatic perturbation theory approach, where you treat this all with diagrams. And the other one is to make the assumption that these reservoirs are weakly coupled to the central system. So the central system is the dot plus the trapdoor. If they're weakly coupled, and the exact definition of weak coupling is a bit subtle, but then it turns out that all of this ugly Keldysh diagrammatic equations reduce down to some very simple rate equations that basically look very classical. So all of the quantum physics disappears, and basically you have four possible states of this central system, with classical transition rates between them, with the transitions either being induced by, so here are my four possible levels, and the white lines are transitions induced by a coupling to the left reservoir, the pink lines are coupling to the right reservoir, and the blue lines are couplings if you have a bath that allows the trapdoor to relax back to its ground state. So if you don't have that bath, which you don't really need, those blue transitions aren't there. And then actually the thermodynamic problem is now solved, because when you look at these equations, they obey local detail balance. And when the system on the left and the right are both in equilibrium at some temperature with some density of particles, which in this case would be given by the chemical potential, if everything is the same in equilibrium on the left and the right, then you see that all of these rates, so the rates to go in any direction along either of these arrows, is the same in both directions. So your system decays to a state where the rates are the same in both directions. So in the end, you have no net flow. So there is no demon here. Okay, there's no net flow from left to right. So that's a formal statement for why this system isn't a demon, why it won't violate the second law of thermodynamics. But it's maybe not very satisfying, because it just comes out of the calculations and you don't have a good intuition about where it comes from. So I probably think actually I might skip this. So I have some other slides on how you do the calculations. So if anyone's interested, feel free to send me ask a question afterwards, or send me an email. So you can do Born-Markov type approximations, which are sort of quite standard. I don't think there's anything very exciting here. You get to a rate equation, which in this case there are four states. So there's some 4x4 matrix you have to deal with, which its elements obey local detailed balance. If you want to go beyond this weak coupling limit, there are ways to do it using these real-time Keldysh techniques. So you can prove not only that you obey the second law in the weak coupling limit, where things are very classical, but also in the strong coupling limit, where the quantum physics is much more rich and there are real roles played by coherences and things like that. So then
I'm sorry, Rob, I think we'll have to move to the conclusion quite quickly.
yeah,
Not,
fine. Yeah,
not much.
no
Sorry.
problem. So then I think, so I wanted to say, so the system's not a daemon, but it can act as a heat engine if the reservoir that causes the trapdoor to relax is at a different temperature from the electrons that are flowing from the two reservoirs. So there's actually three reservoirs. The one that causes the trapdoor to relax back to its ground state, if that's colder or hotter, then the system can generate work without violating the second law, and you can prove that it doesn't violate the second law, but it can produce some work if you want it to. And now I'll come just to conclude to the way to see that this system in an intuitive way doesn't violate the second law. So let's go back to this classical trapdoor. So I think the right way to see it is that to think about a process and its exact time reverse. Okay, so for every process that's like the green arrow here, there is another process that is like the red arrow here. So, so the green one pushes the trapdoor open, but the red arrow is the trapdoor was already open, it is closing, and it pushes a particle through the trapdoor that maybe wouldn't have gone through the trapdoor if it hadn't been hit and pushed through the trapdoor by the movement of the trapdoor. So then once you see that, once you compare these two trajectories, which are the exact time reverse of each other, I think it's easy intuitively to convince yourself that when the two sides are in equilibrium, the processes should come with equal probability. And that for me is the way to see at an intuitive level why this trapdoor will not, even though it has an asymmetry, it opens to the left but not to the right, it will not cause a violation of the second law. The flow from left to right and from right to left in equilibrium will still be exactly the same. So the average flow will be zero and there will be no violation of the second law. And so that's exactly what you can show analytically in the quantum case. And I assume you can also do it in the classical case, but actually the classical case is, as I said, is a bit harder because you have a full degree of freedom and not just a two-level system for the trapdoor. So I haven't done it. But I would be very surprised if it doesn't immediately emerge from the equations to see this process that the green and the red processes shown here should come with the same probability. And of course, then if the pressure is higher on one side or the other, the corresponding process, its probability becomes a bit higher. But that's just normal flow from high pressure to low pressure. So with that, I will conclude. We expect the second law to be illusion, otherwise perpetual motion machines would exist, but sometimes this illusion is good. And in this case, in the trapdoor, it took me quite a long time to understand why it wouldn't violate the second law, even if at no stage did I believe it would violate the second law. To see the intuitive reason was more subtle. And then, of course, you know, the second law is just one of many subtle bounds which we've been hearing about, like TURs and KURs and things like that. And so there's lots of interesting questions probably for these sorts of slightly paradoxical systems in that direction as well. So thank you very much.
Thank you.